So hello again, this is Galen Pickett, Physics 151, Cal State University of Long Beach. Today I want to talk about Section 8, Chapter 4. This is where the friction force approximation, the kinetic friction approximation, is laid out. And friction in the ancient world was considered to be a fundamental interaction for how physical objects interacted, but really it's not. It is a consequence of the fact that, so here I've got an object that's sitting on a table. This force is a part of the contact force, and it's just a consequence of objects made out of atoms in contact with each other. So what happens when you press the object into the surface is there is a depression that will certainly generate a normal force. I don't think there's any, you can see how this yellow thing has been pressed downwards. That would give a resultant force upwards that we call the normal force. But if I tried to move this block to the side, there would also be a lateral force, and that lateral force would give the name friction. And the size of the friction force depends on how deeply this object has been pressed into the surface. So if there's a bigger normal force, there's going to be a bigger friction force. And the constant proportionality there is called the kinetic friction coefficient. So here's the problem that I want to consider. I've got an object, there's mass m, and it's sitting on a surface with friction, so there's the object with mass m, and there is a force T that I'm using to pull it, so like say a rope, and I want to know what is its change in momentum. What is the rate at which its momentum is changing? So let's approach this from the point of view of our problem-solving strategy. The director says this is a momentum principle problem. We've got the kinetic friction approximation. The things that we're given here, mu k is given, the mass is given. Let's say that g is given, and the tension is given. The unknowns, dp, dt. I do not know the rate at which the momentum of this object is changing, and I'll just give that a circle. So now I've got a target, I've got a plan, I've got a list of the knowns and the unknowns. There's one more unknown in there, so let's put some more unknowns that I don't know, I don't have in the statement of the problem. I don't have the friction force, I don't have the normal force. So let's see how far we get. Investigator. The first thing is to make a net force diagram. If you've taken physics course before, you sometimes call this a free body diagram, but it's a net force diagram. So there is the object, and now on this object, so the system is the object, the surroundings are equal to my force, which is T. I've got the normal force, the friction force, and its weight. Those are all the interactions that are acting. So I'm going to put each one of those on this diagram. There's a T. That's the force that I'm using to move this object. There's a normal force. There's a weight force, and there is a friction force. So I've got all the directions here, and let's say there's the x direction, there's the y direction, and now I can say the momentum principle. dp dt is F net from the surroundings. Now another way to say this, if we're talking about a finite time, we could write delta p is equal to F net times delta t, but really all that's happening is I'm dividing both sides by delta t, and then taking the limit as delta t goes to 0. So I've got dp dt is equal to, I'm going to write it down algebraically, the normal force plus the tension force plus the friction force plus the weight. And when we write that out in components, the normal force has got 0 in the x direction, n in the y direction, 0 in the z direction. The tension force has t in the x direction, 0 and 0. The friction force has minus f in the x direction, 0 and 0. And the weight has got 0 minus mg, 0. So we add those things together. We have dp dt is a vector with x and y components. I take the x components, that's 0, t minus f and 0. So that's t minus f. The y components, that's n, 0, 0 minus mg. So n minus mg and 0. So that I'm going to call equation number 1. But it's a vector equation. 0 accounts for 2 equations. I do not know f and n. There is one thing I do know about dp dt. I know that dp dt y is equal to 0 because the box does not leave the surface. So that helps me solve the problem. The last thing I need is the relationship between f and n. F and uk n like so. Equation 3. So what do I have here? I've got dp dt has got 2 unknowns in it, but I've got the friction force, the mg, and the y component. So those are 3 unknowns and 3 equations. So now I can go into execute, solve. If I look at the y component of equation 1, I get 0 is equal to n minus mg. So it says that the normal force is equal to mg. So the normal force is mg. I can substitute that into equation number 3, the kinetic friction approximation, and get that the friction force is equal to mu k times mg, and I'll put that back into the x component of equation 1. So I get dpx dt is equal to tension minus mu k mg. And now I have no unknowns left. That's my answer. Skeptic review. First, let's check the units. The units of dpx dt should be newtons. Well, the units of tension are newtons, so I just have to check the units of this thing. The units of mu k mg are, well, mu k is just a constant of proportionality between 2 forces, so it's dimensionless. M has units of kilograms. G has units of meters per second squared, and that is a meter. So it passes the unit check. And there are no unknowns. So now let's check some behaviors. We could have a case where tension is equal to mu k mg. That would say that dpx dt is equal to 0. So here we have a case that's a little curious. The tension is not 0, but the object moves with a constant velocity. So what's up with that, with the momentum principle and what we've been calling Newton's first law? And this is a common misconception. You assume, because of a problem exactly like this, that you need t in order to move. That if there is no t, that the object would just be standing still. And that's not correct. If there is no t, then the object will slow down. It won't, and eventually it'll come to rest, but it doesn't have to stay at rest. So if an object is moving like so at a constant velocity, the momentum principle tells me, so here's the breadcrumb trail data. There's no interaction, no net interaction. Well, I've got my tension T and the friction force backwards. When those things cancel, then you can move an object at a constant velocity.